I'm going to solve question 1 from worksheet 0328.pdf that we did on March 28th. I have the problem statement here from the worksheet. We have a horizontal segment and a vertical segment, and they are interconnected by a quarter of a circle, and we have a current flowing this way from left to right and then around the corner and then down. And mysteriously, we're not asking any questions about what that current does beyond that. Of course, it's non-physical to have a current that just starts out of nowhere. But we'll take it at face value. We want to use the Biot-Savart law to figure out what the magnetic field is at this point P. So if you just want my solution, I already have that written out. So my solution is already written out in the slides from March 28th in this PDF, which will be linked from the notes for this video. And you can see my handwritten solution over here on the left. But I think the benefit of this format is so that I can talk aloud through my solution. So I start by defining a coordinate system. I put the origin at this point P where we want to evaluate the magnetic field. The length of this magenta segment is L. The length of this green segment is L. And the radius of curvature of this blue segment is R. So then this point is x equals minus L, y equals plus R. This point is x equals plus R, y equals minus L. So let's go 1, 2, 3. So we'll evaluate the horizontal segment's contribution to the magnetic field at P, and then the then the vertical segment, and then finally the curved segment. Okay, so horizontal segment, I'll call that contribution H. Vertical segment, I'll call that contribution V. And then the curved segment, somehow I'll call it R, or radius. So the Biot-Savart law, which I think is one of the most confusing points in the course, says that the magnetic field at some point P is mu naught over 4 pi times the line integral of I, that's the current, dl, that's going to be the direction that we travel along the current, and it has to be in the direction that the current flows, cross product with r hat. What r hat we mean is worth thinking about, and then divided by r squared. So this r hat is the direction of this little r. And by the way, we almost always use the trick in these problems that r hat equals this vector r divided by the magnitude of r. So therefore r hat over r squared is just this r vector divided by r cubed. And that's why you always have like something to the 3/2 power in the denominator in these problems that involve integrals. So what do we mean by R? I'm going to pick a little point somewhere along this horizontal line segment. So we're just evaluating, actually we're just going to evaluate the horizontal part for now, and the horizontal segment of the current. And the coordinates of this little point along the path is, this is x, although x is less than 0. So I could say x equals x, whatever, here's x. And then we have y equals r. And then the point P, so this is like our little point here, which is the source of the field, so it's kind of like the source point. And then the point where we're evaluating the field, where we evaluate b, that's like p equals, actually now, see, that was kind of convenient. We made p just be the origin. You don't have to make p be the origin, but in this case, the integrals that we get will be less messy if we make p be the origin. So now I want the vector from the source point to the point where we're evaluating the field. I like to do this in unit vector notation. So this vector, this is this vector r. So this vector r points from the little source chunk to the point where we're evaluating the field. There's going to be another vector in a moment, which is like the vector along the tangent to the flow of current. So I'm going to do this whole vector r instead of just the unit vector r hat. And then that means we're going to put r cubed in the denominator, because this thing r hat that we want is actually this r vector we're going to work out divided by the magnitude of that r vector. And then in any case, we have another 2 powers of the magnitude of that vector in the denominator. So I'm going to say that this vector r, this is from the source point to the point where we evaluate the magnetic field. Okay, so we want to go to the right, so it's going to have something, this is like I hat, and how far is it from here horizontally to here? That's the horizontal part. And it turns out to be minus x, because it's really I have to give this point a name. I'm not sure what to call it. I'll call it S for source. How about that? So this is like, you see x p, that's where I want to evaluate the field, minus x source I hat. And then there's y p, that's where I want to evaluate the field, minus y source times j hat. There could be a k hat also if we were working in 3 dimensions, but this current is confined to the xy plane, even though the magnetic field will turn out to be in the z direction. So I'll just leave it in 2 dimensions here for this. So this xp is just 0. You see, here's the origin minus x, the source point. The source point, I'm just calling this x. See, this is like x comma plus r. X happens to be less than 0 here. So x is going to go from the range x equals minus L to x equals 0. That's I hat. And then plus, now y, the point we're evaluating the field, is 0 also, because that's the origin. And then x for the source point is just plus r. So there's j hat. So this is minus x times I hat, and then minus r times j hat. R is a positive quantity, so the y component is downward. That makes sense. You say, why do I have a minus sign here? Well, negative x is a positive quantity. You see this thing minus x, because x is less than 0, negative x is a positive quantity. So this is actually a positive amount in the x direction and then a negative amount in the y direction. Okay, so then the magnitude r is like the magnitude of this r vector, is square root of x squared plus r squared. And then if I wanted to turn this into a unit vector, I could say r hat equals this thing. This is like r vector over r, which is minus x I hat minus r j hat divided by the square root of x squared plus r squared. Okay, and then, but the thing is, then I also have r squared in the denominator. So you know eventually it's not going to be the 1/2 power, it's going to be the 3/2 power in the denominator, because we have 2 more powers of r. Meanwhile, let's step back and say, what is this first factor here, I dl, and then we can also think about the cross product. So let's figure out this vector dl. So I is just the current. So here is dl. You see dl is going along the direction of the current. So the current is going to the right, so that's in the x direction. So this is mu naught over 4 pi. We can bring the I outside because it's a constant. And we're integrating for this horizontal segment from x equals minus L to x equals 0. So we're going in the plus x direction, so dx will be a positive quantity. So dl is just going to be dx times I hat. So dx is positive. So this is like the unit of length along the line segment. So dx is a unit of length, and then we're going in the I hat direction to the right, and dx is positive. So here is dx I hat, so that's dl, and then there's going to be a cross product with, it's hard to make a cross product that's not confused with an x unless you're typing. And then this vector r hat that we worked out, I wrote it here in purple. This is minus x I hat minus r j hat. And then we want to divide by the square, no, the cube actually, because, right, see this is r hat, and this was the entire r vector. If we really wanted r hat, it would be this thing divided by its magnitude. We have 2 powers of its magnitude here already, so we'll just make 3 powers of its magnitude, and that accounts for our writing r upstairs instead of r hat. So then here is x squared plus r squared to the 3/2 power. Okay, then before we integrate, we can evaluate that cross product. So it's going to have 2 terms. I hat cross I hat is 0 because you have to have the perpendicular components. Like to get a non-zero cross product, you have to pick out 2 components that are perpendicular to each other, so the cross product of a vector with itself is 0. I hat cross j hat equals k hat in a right-handed coordinate system. So that's going to be this. Okay, so this cross product, this is going to give us 0. This cross product, this, is going to give us k hat multiplied by dx and multiplied by minus r. So here is mu naught over 4 pi, and then here's I, and here's the integral x from minus L to 0. So this is going to be in the k hat direction. I hat cross j hat is k hat, and then what is that multiplied by? It's minus r times dx. Minus r is really a constant. Okay, dx. And then downstairs we have x squared plus r squared to the 3/2 power. We can make sure we did that right. So ijk multiplied by minus r multiplied by dx. Okay, that looks good. We could do one more step to pull the constants outside, and then this turns out to be an integral in our integral table. Okay, so this is minus mu naught I k, oh, there's an r also, minus mu naught I r k hat divided by 4 pi, and then we have the integral x is minus L to 0 dx over x squared plus r squared to the 3/2 power. Okay, so this is minus mu naught I r k hat over 4 pi. And I think I remember the answer to this integral. I think it is x over r squared times the square root of x squared plus r squared I should have looked this up before writing it, but I think this is right. So here's minus L to 0. Let me just double check that. So x over r squared square root of x squared plus r squared. Yeah, minus mu naught I r k hat. Okay, good. How about that? We get the same answer I got when I did it in my office. Okay, so we want to evaluate this. So at x equals 0, this is just 0. At x equals minus L, we plug in x equals minus L, but this is the lower limit of the integration, so we have a minus sign to kill that minus sign. So this will just be plus L. So this is right, because the 0 term, that's this, the upper limit of the integration gives us 0, so then we subtract the lower limit of the integration, which is negative. So we're subtracting a negative, so that gives us a positive. So here's minus mu naught I r k hat over 4 pi, and then this is L over r squared times the square root of L squared plus r squared. Okay, and I think there's a little bit of simplification we can do. We can cancel one factor of r. So this is minus mu naught I L k hat over 4 pi r root L squared plus r squared, which is kind of an ugly expression. So okay, we notice that it is in the z direction, minus z direction. It's in the minus z direction. It's into the board. Let's just see if that makes sense. So we have, this looks like my left hand is actually my right hand because the video is reversed. So we have I dl cross r hat that points into the board. So that makes sense. Okay, so this was this first term. I'll copy it down and then we'll work out the vertical term. Now let's work out this vertical segment's contribution. So I called that the magnetic field at point P due to this vertical segment V. I'm going to pick some point that I call S on this green vertical segment. Remember, the current is flowing downward, so we want our vector dl to be tangent to the wire in the I direction, the current direction. And here's my point, x equals r and y equals y. And now I need to draw this r vector from the source point to the point where I'm evaluating the magnetic field. And really this equation is asking for r hat. So again, instead of r hat over r squared, I'm going to write the r vector unnormalized and then divide by r cubed. So this vector from S to P looks like this. So its x component is just minus r. So there's minus r I hat. Its y component should be positive, but remember y is less than 0 here, so it's actually minus y j hat. Minus y is a positive quantity, so this is going to the left and it's going up. That makes sense. And then we have dl is, now we want to think about this. You'd say, naively you would say it's dy times j hat. Well, actually you might say it's times minus j hat. Let's think about what the direction of dy is. So I mean, I think you could integrate either way, but I decided to integrate along with the current. So I'm integrating from y equals 0 to y equals minus L. And when I do that, dy is negative. So I think if I say dl is dy j hat, then this is good. I'm going some unit of length dy dy is negative, so this is in the minus y direction, minus j hat. So I think this is fine. So then we have mu naught over 4 pi integral y equals 0 to L. I is just a constant here. dl is dy j hat, and then cross product. Now this is r hat, so to make up for the fact that we're writing r instead of r hat, I'm going to put r cubed downstairs. So downstairs this will be y squared plus r squared to the 3/2 power. Now this r vector here is minus r I hat minus y j hat. Okay, and when we evaluate this, j hat cross j hat is 0, and j hat cross minus I hat is the same thing actually as I hat cross j hat, because swapping them reverses the sign. I hat cross j hat is k hat. So if I include the minus sign here, then I get k hat. This can't be right because, oh, I see. I'm looking at this term. Yeah. Sorry, I confused myself. I'll edit that out if I actually edit someday. So I'm looking at this term. J hat cross minus I hat is k hat. And what confused me is, gee, I'm expecting this whole thing to point in the minus z direction, not the plus z direction. I think the minus sign is going to come out when we integrate. Okay. So this is going to be mu naught, and then we can pull out the I. We can actually pull out the r. And then actually we can also pull out the k hat. And then over 4 pi, and we're integrating. Okay, what's left? We have dy. The minus sign went away because we had j hat cross minus I hat is plus k hat. We took the r out. We took the I out. I think that's all we have in the numerator. And then we have y squared plus r squared to the 3/2 power. And this is integrating from y equals 0 to minus L. Okay, then we can evaluate that integral. So this is mu naught I r k hat over 4 pi, and then this is going to be y over r squared square root of y squared plus r squared evaluated from 0 to minus L. Okay, so the first term is going to be minus L. So here's mu naught I r k hat over 4 pi. So this is minus L divided by r squared square root of L squared plus r squared. And then minus 0, because we'll plug in y equals 0. Then we get a cancellation of one factor of r, and then we get our minus sign back, which is a relief because we think the magnetic field, we somehow know by peeking that it's going to be in the minus z direction. Also, we know from the, see, if you say IDL cross r hat, see there's IDL cross r hat, it points into the board, so it should be minus k hat, so that's good, we have a minus sign. So there's minus mu naught I L k hat divided by 4 pi r square root of L squared plus r squared. So this should look exactly like the other term. If we did everything right, good. Okay, that's this second term here. Now the third term for the curved part, we can actually do it two different ways. The more straightforward way to do it is essentially to turn it into a multiplication. Because if we draw dl here, dl is tangent, and then r hat is just radially inward. So you say dl cross r hat is always in the into the board direction, the minus k hat direction. So in fact, I dl cross r hat equals, so here's the current, and then dl is basically just like r d phi, and then and that's going to be in the tangent direction, and then the tangent direction is perpendicular to the radial direction for a circular orbit. I mean, this is like a quarter of a circle. So these are perpendicular to each other, so there's no sign factor in the cross product because these two vectors we're cross producting are perpendicular to each other. And then so then we cross product with r hat, the result is just going to be minus k hat. And then we divide by here, then there's actually r squared. So r squared actually in this case is just the radius of curvature squared. And then we actually wanted to multiply by mu naught over 4 pi. So here's mu naught over 4 pi, and then the only integral left is an integral d phi. So this is basically integral, well, I'm going to say, what are you calling phi? I'm going to call this phi. So I'm saying that this little angle here is phi, the angle from the vertical. So we have integral d phi from phi equals 0 to pi over 2. So that just equals multiplying by pi over 2. That's a trivial integral. So this is like the circular component, the r component of the magnetic field at point P. That's mu naught over 4 pi. And then I dl cross r hat is just I r d phi. It's in the minus k hat direction, divide by r squared, so one of those r's will cancel, and then we're just integrating from 0 to pi over 2, so that's just multiplying by pi over 2. So there's mu naught I over 4 pi r, mu naught I over 4 pi r, here's minus k hat, and then we have pi over 2. I think that's all there is. Mu naught I minus k hat, pi over 2, 4 pi r. Yeah. So then there is minus mu naught I k hat over, the pi's cancel, you get 8 r. Okay. And is that what I got before? Mu naught I k hat over 8r with a minus sign. Yeah. So then we have here's at P, the kind of radial component is minus mu naught I k hat over 8r. So then we could combine all these together, and that's the final answer. So yeah, we have this term This is the second term. This was the first term. And then here's the third term. First and second terms are the same. So this is the magnetic field at P equals minus mu naught I L K hat over, so we're just going to double this, it'll be 2 pi r square root of L squared plus r squared. And then there's this other term, here's minus mu naught I k hat over 8r. And then if you want to, you can factor it, because mu naught I k hat over r, for instance, is a common factor. I'm not sure that's worth the trouble, but you can do it if you want. Let me just double check that we didn't write anything down incorrectly. So minus mu naught I L k hat over 2 pi r root L squared plus r squared, that's fine. And then that other term is minus mu naught I k hat over 8r. That's fine. I could show you how to do the circular arc part with unit vectors, even though this is really the much simpler way. So you can stop, this is good, but if you want to see me do it with unit vectors, you can keep going another few minutes. Okay, let's reproduce this result, so just the curved part of the segment, this little curved segment. So I drew this a little bigger over here, and here's my source point S, and here is my point P where I want to evaluate the field, and the current is flowing this way, kind of clockwise, so my dl has to be the tangent vector oriented clockwise. So we're going to say this magnetic field at point P for this kind of curved segment is mu naught over 4 pi integral. I'm going to integrate phi equals 0 to pi over 2, because we're measuring phi from the y-axis clockwise. That just lets me do a positive d phi. So then I want I dl cross r hat over r squared, which is going to be the same as I dl cross, yeah, actually this time I really am going to write this unit vector r hat instead of a vector big R. So, I mean, instead of just a vector r, it's going to be a unit vector r. So here's mu naught over 4 pi. I can pull out the constant I, and then I'm going to integrate. Okay, so dl, what is dl? So when I'm at, okay, if phi were 0, dl would be in the I hat direction. So I think I have cosine phi times I hat, because if the cosine term is what I would get if phi were 0. And then if phi were 90 degrees, I get the j hat term. So this is minus j hat. I get the sine phi term. So this is minus sine phi j hat. And then it's actually times r d phi is my unit of length for dl. So everything I wrote here so far is just the dl vector. So dl is r d phi times I hat cosine phi minus j hat sine phi. And yeah, again, the way I usually think about that is the cosine term is, the coefficient of the cosine term is what I would get if phi were 0. And the coefficient of the sine term is what I would get if phi were pi over 2. Because for phi equals 0, you have cosine is 1 and sine is 0. And for phi equals pi over 2, you get sine is 1 and cosine is 0. Okay, now cross product with r hat. That's the radial direction. So if phi were 0, the radial inward direction would be minus j hat. So that's minus j hat cos phi. And then if phi were 90 degrees, the radial direction would be minus I hat. So there's minus I hat sine phi. Let's just think about that. So 90 degrees. So there's minus I hat sine, yep. And then there's minus j hat, yeah. Okay, and then r is just r. And this really was a unit vector. There was no, see, the magnitude of this thing is 1. So this is just r hat, whereas before we were writing r including, oh, this is r squared, r including its magnitudes, we had to write r cubed downstairs. We only have to write r squared downstairs because this is already a normalized vector. It's a unit vector. Okay, so I think this cross product is actually going to turn out to be pretty simple. Okay, so this is mu naught I. We don't need this. This r is only r downstairs. So mu naught I over 4 pi r, because r squared cancels this r. So we cancel the square, we cancel the r. And then we're integrating phi equals 0 to pi over 2. And then this cross product is going to be a little bit silly, you see. So, okay. So I cross j is k. So this is going to be cosine squared phi. And then times, okay, so just bear in mind, there's going to be I cross j is k. So this is a minus sign. So this is all going to be minus k hat. But then let's look at the other term. You want me to write this out here. Cosine phi I hat minus sine phi j hat cross product with minus j hat cosine phi minus I hat sine phi. Okay, first term, cross product first term, is minus cosine squared phi. So there's the minus sign. And I cross j is k. So there's k hat. First term with second term, I cross I is 0. Second term with first term, j cross j is 0. Second term with second term, this is j cross I is minus k, and then we have, that's one minus sign, and then we have another minus sign, and we have another minus sign. So we have 3 minus signs. That's an odd number of minus signs. So there's minus sine squared phi k hat. Cosine squared phi plus sine squared phi is 1. So this just equals minus k hat. Okay, so right, so here's cosine squared phi plus sine squared phi minus k hat. Did I miss anything? Oh, there's d phi. Okay, we already took care of the r. Yeah, okay, and this is just 1. Okay, so this is mu naught I over 4 pi r. There's a minus sign, there's a k hat, and then all we have is the integral d phi from 0 to pi over 2. That's the same thing as just multiplying by pi over 2. So I'm going to do something that people always hate if they're taking notes. I'm going to erase, and I'm going to say multiply this by pi over 2. And that gives us minus mu naught I k hat over 8r. Because, okay, 4 times 2 is 8. Pi divided by pi is 1. Which is the same thing we got here. That's good. Okay. So you can see that in this case, the unit vectors just made things unnecessarily complicated. It was actually much better in this case just to say dl cross r hat is minus k hat. And then you notice that you're integrating a constant. You're just integrating d phi times nothing, so it's just multiplying by pi over 2. Anyway, this is like a kind of messy Biot-Savart law problem. So it's kind of good to know how to do them, even though maybe they aren't the most important part of the course. I think the unit vector part is the trickiest, and it's especially tricky because unlike the electrostatics problems using Coulomb's law or working out the electric field, you additionally have this kind of messy cross product. So like this r hat vector is familiar from the electric field calculations, but then there's this dl cross product part, and it's a line integral. So maybe that makes it even a little bit harder to conceptualize.